Today, we're going to discuss about nonlinear programming. Okay. If you remember last time, our focal point was on linear programming, right? In case of linear programming, your objective functions is linear function, of course, and all the constraints are linear function also. Yeah. While they can be equality or inequality constraint. Okay, but in case of nonlinear programming, well, we have a case where objective function can be linear, but objective function, no, constraints are nonlinear, or, well, both of them are nonlinear. Okay, or while in some case, our objective functions is nonlinear, but the constraints are linear functions. Either case, wow. We classify those problems as nonlinear programming. Okay, so you see that it's quite huge, and it's quite difficult to handle them effectively. So, but the basic idea of nonlinear programming follow this step. Well, the algorithm starts from initialization. We start the algorithm using initial feasible solution. Okay, and we follow the iterative process to evaluate the objective function and just adjust decision variables, well, in a way that seeks to improve the objective function. For example, if you start from any feasible solution, right, and you evaluate the objective function of that point, and then you find the direction where your aim is to improve the objective function. If you want to maximize it, you find a new point where objective function increase. Okay, and we repeat this step, iterative process, until we reach the terminal criteria. Okay, which is the last step, termination. Okay, the process stop when no significant improvement can be made to the objective function. Okay, it should be stopped, right? Okay, so what's a challenge in nonlinear programming? Well, nonlinear programming can be, well, it's quite challenging due to the nature of nonlinear function. First, maybe they may involve multiple local optima, right? You can have multiple optimum point. That means, well, there can be points that look optimal if we only consider the nearby point, right? Local optimum point, but it's not the global one. Also, the shape or landscape of the function can be much more complex than in case of linear programming. Okay, and mathematical properties that help in linear programming, like convexity, may not always present in case of nonlinear programming. Okay, so we start from the very basic algorithm. Okay, the basic idea of the most numerical method of the algorithm to solve nonlinear programming. We start from initial trial point. Okay, let's say x1. Then we find a suitable direction first. A suitable direction that points the general direction of the optimum point. Okay, imagine that you are, well, you are somewhere in the forest. If you want to find the valley, okay, you're starting from any trial point, initial point. You have to go down the hill, right? You look at the slope of the hill. Okay, any direction which point down, you follow that direction. Okay, then find appropriate step length. You fix the direction, you choose the direction first, and then you follow that direction, you move for a certain step length, okay? Movement along that direction S1 or SI, okay? And once you have direction and you move along that direction for a certain length, you reach a new point, okay? You obtain a new point. Once you reach a new point, that new point is xi plus 1 is xi plus multiply of lambda I and si, okay? And then you test whether xi plus 1 is optimum, okay? If that point is optimum, then stop the procedure, okay? Otherwise, set a new I is I plus 1 and repeat step 2, okay? Onward. You see that it's the process is interactive, right? We start from initial point and then we select direction, we choose the step length, and once we reach a new point, the new point should be better than the previous one, right? And then you repeat the process, you find the direction again, you move for a certain direction, certain length, and you get a new point, and you repeat this process until you reach the stopping criteria, okay? Termination criteria. Okay. Well, consider this diagram. Okay, let's say we have a contour of objective function. Okay, contour of objective function. Well, you can ignore the constraint. This constraint which set the feasible region. Okay, ignore them. If we start from any point in this contour, in the surface of this objective function, first we find the direction, suitable direction, and we move along that direction to a certain length until we reach new point. And again, once we reach this point, we find a direction again, let's say this direction, and then we follow this direction for a certain length. We reach x3, okay? We reach a new point, and then you find again the direction and the step size or the length until you reach the new point. You repeat it again until you reach the point where you cannot improve the objective function anymore, then it's stopping criteria, okay? So you see that the iterative process involve two things. The first one, the direction, and the second one, the length. How large of the step we move in each iteration process, okay? And the first one involve the direction, how to choose the right direction, okay? So the efficiency of optimization methods depends on the efficiency of which the quantities of lambda I, okay, step length, and the direction are determined, okay? If you propose a new, the new method to find the direction, of course, you finally develop a new methodology, of course, new algorithm, okay? So the method of finding step length and lambda I are considered here. I will show you some basic algorithm to find the direction and also the step length. Okay, so we can broadly classify the technique to two types. The first one is analytical method, like using differential calculus method. And the second one, numerical method. Okay, and for numerical method, we can broadly classify them to elimination method and interpolation method. Okay, I will start explaining about the elimination method first, and then you will see how we can scope down the optimum point. The first thing, I should introduce you the unimodal function first, the idea of a unimodal function. A function f is unimodal, okay? If x1 is less than x2 and less than x star, implies that if x2 is less than fx1, and the second one, x2 is greater than x1, but less than x star, imply that if x1 less than fx2, where x star is the minimum point. Well, maybe while you're not, if you are not familiar with mathematics, I will try to explain you graphically. Unimodal function is, well, in the area of interest, for example, during A and B, you see that there is only one minimum point, okay? If the function is unimodal, it looks like this. While we have in the area of interest, we have only one minimum point or maximum point. It's all right. Okay. This is the, what is it? The important feature of unimodal. Okay. If we say that, well, this function is unimodal, okay, that means in the scope, in that scope, we have only one minimum point. Okay. So, well, can you tell me this function? Is it unimodal or not unimodal? For A, it's clear, right? It's unimodal. What about B? It's unimodal, right? You can check with this expression. I mean, mathematics. It's clear that, well, this statement define the unimodal function. Okay. What about this? What about C? Yes, C is also a unimodal function, right? Now, if we know that in the area of interest it is unimodal function, then I tell you, I give you this figure. From 0 to 1 is unimodal function. I ask you one question. If I choose x1 and x2 in the area of interest, and I evaluate the function of x1 and x2, I got f1, f2 here. Can you tell me if we are looking for the minimum or maximum, this one? Minimum point. Can we be sure that some part, any area, it's not the, what's it? We don't have minimum point in that area. Can you guarantee some region that we will not have minimum point in that area? Which one? Which area? No. I mean the area. It must be area. From where? We can eliminate some area, right? Which area we can eliminate? From x1 to x2? No. 0 to x1? No. x2 to 1. We can eliminate, we can guarantee that minimum point will not lie in this area, in the area from x2 to 1. You got the point? Okay. we can eliminate this area, right? Because, well, the function can look like this, right? Go down and up. Okay, we cannot eliminate the area between x1 and x2 because the function can look like this, right? Okay, however, there's no chance that the minimum point lie between x2 to 1, right? Okay, what about B figure? From 0 to x1 we can eliminate it. Okay, what about this? C. We can eliminate both this area and this area, right? From 0 to x1 and x2 to 1, right? Okay, so you see that if we have information that the area of interest is unimodal, you just, well, you test 2 points. You can eliminate part of the area out. You can scope down the area of interest. Okay.
Sir, can you show why like for the first figure A, right? Why we can eliminate the right side? Like why is it impossible?
Which the right side? The right side is x2 to 1?
Yeah.
We should eliminate x2 to 1.
Yeah, but why? Like why is it impossible to have a minimum here?
Oh, because it's unimodal. So you see that x1 is less than x2, right?
Yes.
So if we have another minimum point here, the whole area is not unimodal anymore. Because you have to go down again, right? The function must have, you have inflection point somewhere, because you have to go down again from x2 to 1, right?
Yes.
Yeah, so we can eliminate this area x2 to 1.
Sir, can you define unimodal now? I'm starting to get confused. Like,
well, unimodal here, A, B, C, they are, well, unimodal.
because there's a because there's a point that is lower.
No, for unimodal, remember that it's uni mean 1, right? You have only one minimum point in that area. Okay.
Oh, okay.
Yes, that is.
That's it. Like one minimum point in the area is called unimodal.
Yes.
Oh, okay. So.
Okay, so well, I already explained that. Yeah, from 0 to 1, right? You test F1 and F2. If we have, well, if it looks like A, you can eliminate x2 to 1. Again, if, well, the test look like this, you can eliminate this, the left-hand side. And if it's, well, the results show like this, so you can eliminate 2 parts, something like that. Okay, so that is the basic idea. Okay, you see that if you repeat this algorithm, you can scope down the area of interest smaller and smaller by testing 2 points at each step. That is very basic algorithm. Okay, now we start from unrestricted search. Okay, we call it's the search with a fixed step size. Okay, and imagine that we are now follow the one dimension. Okay, the objective function contains only one decision variable. Okay. Okay, so the algorithm here, we start from initial guess point x1, and then we find f1, and assuming a step size of s, And then we locate the x2, which is x1 plus s, and then we find f2. Okay. And if f2 is less than f1, okay, we follow this idea. Okay. You start from x1, right? You have step size, certain step size, fixed step size, and then you obtain x2 and then test it. Okay. Yeah, you can read that in the slide. Okay. Wow. Let me explain from the example. Okay. For example, we're going to minimize this objective function over the range of -5 to 5. Okay. So the idea of the fixed step size, let's say the step size is 1, right? So we divide the whole area, okay, with a certain step size, and then, well, you evaluate the objective function at each point, okay? And from this testing, this result, can you tell me the area where the minimum point should lie?
-2 and 0.
Yes. Between -2 to 0, right? Because if we look at the minimum point here, we see -3 and -3, right? The objective function. So we know that the whole function first, the whole function is unimodal, right? We assume that. So our minimum point must lie somewhere between this -3, which the decision variables are -2 and 0, right? You see that in one step, we can eliminate part of the area of interest. Then you repeat this step again, starting from -2 to 0. Well, you repeat the step, and then you can narrow down the area of interest, okay? Okay, another example is using heuristic search with a fixed step size of 0.1 starting from lambda at 0. Okay, of course, you can use Excel if you want, okay? Define the step size and then, well, evaluate the objective function, and then we see here it's inflection somewhere here. So minimum point should lie between 1.9 to 2.1, right? Somewhere around this area. Then we can scope down from 0 to, yeah, we can narrow the area of interest, okay? Now we move to the next algorithm. The next algorithm is search with accelerated step size. You see that previously with fixed step size, the algorithm is quite very simple, okay? But its major drawbacks, it's very, what's it? Slow, okay? And consume large computation because you have to evaluate the objective function again and again, right? So this involves a large amount of computational work, okay? So an obvious improvement can be achieved by increasing the step size, okay? And, well, this is an algorithm. I'm going to explain you by using the example. From, imagine that we consider this objective function. We try to minimize it over the range of -5 to 5, okay? We start from initialization. The starting point, it's -5. And initial step is 1. Scaling factor is 2. And then we evaluate the next point, okay? And since, well, the next point is less than fx0 plus delta x, the next point is less than the current point. So we continue, okay? And we accelerate the algorithm by double the step size, okay? Because alpha is greater than 1, right? You multiply with alpha, and then delta x becomes 2 this time, okay? And we update the point again and check. You repeat it. If it's still, the next point is smaller than the first point, than the current point, you repeat the algorithm and you accelerate the step size, okay? Increase the step size. Okay, any questions? We move to the next algorithm. We call it exhaustive search. For exhaustive search, well, of course, we work with the interval, okay? Let's say we have interval xs to xf, okay? And we know that our minimum point lies somewhere between xs to xf, okay? And we want to divide this interval into, well, n+1 compartment. What we going to do? We know that we call it uncertainty of the length, interval of the uncertainty of the length. Okay, it's the interval between xs to xf. We call it the length. Okay, and from this length we divide. Okay, it depends on how many points you want to evaluate for each step. In this case, we evaluate from, well, how many points we evaluate? Yes, 8. Okay, and you see that we divide the whole area, the whole interval into 9 steps, right? And at each iteration, you evaluate each point. So it can be look like this, right? Okay, this is one example. And then, well, we know that because we found that this one is the minimum point. However, well, our minimum point can, well, be not this point exactly, can be somewhere around here or around here. Okay, so we can narrow down from xs to xf to the interval between x5 to x7, right? And you see that from starting interval of L length, the length of L, the next step, we narrow down to 2L0 divided by n+1, right? Because we evaluate 8 points. We divide it to 9 steps, right? Okay. And 2 here because we have to consider 2 of it. Okay. It can be here or here. Depends. Okay. Any questions? Yes. Is the number of points we evaluate at each step.
Sir.
Yes.
So the new L0 becomes x7 minus x5.
Starting from x5 to x7, right?
Oh, so
The
why do we?
interval.
Yeah, so why do we need to multiply by 2 if the intervals are
Yes,
already?
because it's not one interval. You see that each interval, each small interval is, what's it? The L0 divided by n+1, right? Yes.
Yes.
And you see that we cannot be sure whether our minimum point lie between x5 to x6 or x6 to x7.
But won't we already divide the x5 to x7 into 9 intervals already? Because L0 is x5 to x7, right? So if we divide by 9, we will also get this 9 interval.
I lost you. I cannot get your point. You
Uh,
see, we starting from XS to XF, right?
yes.
And we divide the interval to 9 area.
Yes.
Yes?
Yes.
Okay. And you see that we evaluate the function, the objective function, and it looks like this. And you see that from the definition of unimodal, we cannot guarantee that the minimum point lies between x5 to x6 or x6 to x7, right?
Yes. Yes.
Yes. So
Yes.
the interval for the next step is not L0 divided by 9, but it must be 2 of L0 divided by 9, right?
L0 is x5 to x6 or
No, L0 is xf, xs to xf.
oh.
Okay. So the next step, of
Oh,
course,
I see. Oh,
yeah.
okay.
In the next step, the L0 becomes x5 to x7. But in the beginning, at the beginning, L0 is from xs to xf. Okay. So you see that we have to trade off. If you want to, well, if each step you evaluate so many points, of course, it's converge faster, but you have to well, compute. You need more computational load for each step. Okay. For example, this function again, we use exhaustive search in this interval from 0 to 5. Okay. Let's say our n is 10. Okay. And of course, we start from 0 to 5, then L0 is 5 in the first step. Okay. And you evaluate the objective function. It is clear that from the first iteration, our minimum point must lie between 1.5 to 2.5, right? And then from this interval, again, you divide it to 10 section. No, not 10 section. 11 interval, okay? N is 10. And then you can narrow down the area of interest, okay? You repeat it again and again, you see that it's smaller. The area of uncertainty becomes smaller and smaller. Or can we break for 5 minutes? Okay, please. We break for 5 minutes. Okay, so we move to the next algorithm. Okay. This one called dichotomous search. Okay. For dichotomous search, we need only 2 experiments. Okay. And well, 2 experiments are placed as close as possible at the center of the interval. Okay. And well, x1 is L0 divided by 2, half of the L0. And you move to the left by subtract it by delta over 2. Okay. And what about x2? x2 is from the half of the interval, you move to the right. Okay, you add by delta plus 2. And you see that from the interval we look at the middle part, okay, at the center. And we need 2 experiments. And those 2 experiments cover the center point, okay? And the distance between x1 and x2 is delta, okay? That means, well, we start from the center point, which is L0 by 2. And we subtract by half of the delta, okay? And for x2, we add delta over 2, okay? And you see that the new interval of uncertainty is given by L0 over 2 plus delta over 2. Okay. For example, if we minimize this objective function by using dichotomous search, okay, in the interval of 0 to 5, and with certain delta, okay? So from the interval from 0 to 5, okay, at the beginning, at the initial, we know L0 is 5, okay? So those 2 experiments should cover the center point, right? So where is the center point? Center point is 2.5, right? Actually, for the dichotomous search, you don't need 2.5. You don't need to evaluate this point, the center point. Okay? Just evaluate center point, subtract by delta over 2, and center point plus delta over 2. Okay? Half of the delta, and subtract by half of the delta, and plus half of the delta. Okay? And then from this, you look at the objective function, you can eliminate some part. Okay? And from here, well, we know that our minimum point should lie between 0 to 2.5, to the center point. Okay? And then we repeat again and again. Okay? So we can narrow down the length of the interval of uncertainty. Okay, the next algorithm is interval halving method. In the interval halving method, exactly 1/2 of the current interval of uncertainty is eliminated at each iteration. Okay, so it requires 3 experiments in the first stage, and after that you need only 2 experiments in each subsequent stage. Initial interval, let's say, well, our initial interval is A to B, okay? It's L0, it's A to B. We divide it into 4 equal parts, okay? We label the middle part as x0, and the quarter interval x1 and x2. Okay. Then we evaluate the objective function at each point, at each part. Let's say this one. The middle point is x0, right? On the left hand side is x1, is x. The right hand side is x2. Okay. Then we evaluate three points. Okay. F1, F0, and F2. And from the result, if we get this result, we can eliminate the right hand side part. Okay. If the result looks like this, we can eliminate the left hand side part. And if you got this kind of result, we can eliminate this part and this part. And you see that for any case, we can eliminate half of the interval, right, in each iteration. Okay. For example, this one, we divide it into, well, 3. First one, we need 3 points, right? 1, 2, 3 points. And then we can eliminate half of this area, right? From the interval is 5 at the beginning. Then in the next iteration, the interval becomes 2.5, which is half of 5, right? And the next iteration, the area of interest, the interval of interest becomes 1.25. Okay, you repeat it. Each iteration, you can get rid of 50% of the interval. Okay, so the uncertainty area becomes smaller and smaller. Any questions? Any questions? Yes. 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 But we limit ourselves only the one-dimensional problem now. Okay, then we move to the next one, quadratic interpolation method. This one, this algorithm belongs to the interpolation algorithm, not elimination algorithm. I show you at the beginning that here we have elimination method, right? And interpolation method. For elimination method, of course, you have an area of interest and then you eliminate some part out, okay? But for interpolation method, you start from one point and then you interpolate to obtain a new point. Okay? We start from the simple one, the simplest one, quadratic interpolation method. The idea is once we have initial point, we can approximate the shape of the objective function as quadratic function. Okay. And you know, quadratic function is unimodal, of course. And the good things that you approximate the objective function as quadratic function is we know exactly the minimum point of quadratic function, right? Because quadratic function is in this form, right? A plus b lambda plus c lambda square. And we know that the minimum point must be at this point minus b over 2c, right? So if we start from any trial point, at that point, we approximate the quadratic function, then you can obtain a minimum point, approximate minimum point. And once you know that the quadratic function is only the abstract of only the estimate function, right? Because we estimate the objective function as quadratic function, but our objective function is not quadratic. Of course, in the next iteration, we move to the new point, closer to the minimum point, and we approximate again as a quadratic function, and then you obtain the new point. Okay, you repeat it process again and again until you cannot improve the objective function, and then the algorithm stop. Okay. The question is how to approximate how to obtain the approximated quadratic function. To evaluate ABC, we need 3 points, of course. We need 3 points. So from that 3 points, we can approximate the ABC, which is our objective function, approximated objective function, which is a quadratic function, of course. Then we can find the minimum point. Okay, I will show you an example. This one. We use quadratic interpolation method. Okay, we start from 3 points, ABC. This 3 points. Then we evaluate FA, FB, FC, right? Because we need those FA, B, FC in this formula. Okay. Then we obtain ABC. This ABC. And from this ABC, we can find the minimum point, approximated minimum point at each iteration. Okay. So we obtain this point. And once we obtain the point, then again, we need 3 points, right? We can, because we know that the new point, it's 1.28 something here. So, well, we can select A, B, right? And introduce from the previous iteration, and you introduce new point here. Okay. So you don't have to re-evaluate FA and FB function, objective function at 0 and 2.5 again. You need to evaluate just the objective function at the new point. And then, well, you can approximate the quadratic function again, and then find the new point. Okay. You repeat the process again and again, you obtain the solution closer to the minimum point. For those who are interested in the MATLAB code, I gave you already in the line group. Okay. The next one is cubic interpolation method. For the cubic interpolation method, we, instead of approximate the objective function as quadratic function, This time we use cubic interpolation. Okay, cubic function. Okay, this is the form of our cubic function. And in case of cubic function, because we have 4 parameters instead of 3 parameters, okay, so we use the value of that objective function, the objective function at one point and derivative at that point. Okay, we need at least 2 points. Okay, because we need 4 information, right? Because we're going to find these 4 parameters. That means you need at least 4 information. So we need only 2 points. But the information we need is the objective function and the derivative. Okay, at those 2 points. Once you obtain the parameter, then you can find the minimum point of that cubic function. Okay. Yeah, we can demonstrate the algorithm in this example. Of course, I show you the Excel. From A and B, starting A and B, we evaluate the objective function and derivative of the objective function, and then calculate ABCD, right? And then from ABCD, you obtain the new point. Okay, again and again, repeat them. Okay, any questions?
No, select from the minimum point.
Minimum point? Yeah. This one, minus C plus root of the, well, square C minus 3 BD, okay, over 3D.
The minimum of 4.
No, we have only, we use only 2 points, A and B. Okay, we start from A and B, right? A and B. But we use information of the objective function and derivative of the objective function. Then we find the 4 parameters. And from this 4 parameters, A, B, C, D, we find the minimum point.
Sir.
Yes?
Why do we need to find like the small a? When do we use it?
You don't need it. I know, you don't need it.
Oh, I see.
Because in this formula, we don't have A, right? The same in quadratic also. You let me see. Yeah, we need only the B and C, right? We don't need A. Okay, so we move to the next algorithm. The next algorithm is Newton method. We consider the approximation of the function. Let's say we have objective function f, okay, if lambda. If we want to approximate this objective function as a quadratic function, you see that if we use Taylor series expansion, from Taylor series expansion, this objective function can be written around the fixed point lambda I. Okay, let's say we have a fixed point of lambda I, right? We can write the function, okay, by using 2 terms, and it becomes a quadratic function, of course. Yeah. Quadratic function, of course. And what do you need here? You need only one point, right? You need only fixed point lambda I. However, you need derivative f prime here. And you need the second order derivative because we're going to use the quadratic term. Okay? So if we rearrange this again to obtain f, sorry. We find the derivative of this function. The derivative becomes f lambda, the derivative of f, okay, the objective function of the approximated objective function becomes f prime, okay, lambda I from this term, okay. This term becomes 0, right? Because it's a constant. This term becomes f prime lambda I, okay, because derivative of this term become 1, right? And for this one, it becomes f double prime lambda I times with lambda minus lambda I, okay? And you know that the minimum point must be, what's it? The derivative at the minimum point must be 0, right? From the basic classical theory, okay? The necessary condition at minimum point, derivative must be 0. So we take this becomes 0 and rearrange again. So you can write lambda as a function of lambda I. Okay. Right? You can write lambda as a function of lambda I. And you see that we can say that lambda becomes a function of lambda I. Okay, from this you rearrange just only this expression and you obtain lambda I plus 1. The next step becomes lambda I subtract by ratio of f prime lambda over f double prime lambda. Sorry, lambda I, okay? So if you start from any trial point and you evaluate that lambda I, subtract by the ratio of derivative and second order derivative of that point, you get a new point. Okay, this is an idea of Newton method. And remember that Newton method is based on the approximation of the objective function as quadratic function. Okay, you see at the first line. So if our objective function is quadratic function, we can reach the minimum point in only one iteration. However, if it deviates from the quadratic function, of course, it takes some iteration before it moves to the minimum point. Okay. The drawback of the Newton method is we need derivative and second order derivative. In some function, it's quite difficult to find the analytical solution of the derivative and second order derivative. To solve such problem, we can calculate, estimate, because anyway, we're going to estimate the objective function anyway, right? So we can estimate the derivative of the objective function by using numerical method. Okay, here. Second order derivative also can be approximated by using numerical. Okay, and if you use the numerical approximated derivative and second order derivative, we call the algorithm as quasi-Newton method. Okay, so that means, well, you use this expression to find a new point, right? But for f prime and f double prime, you use numerical value of it. Okay. And this is the example. At each iteration, oops, sorry. Okay, at each iteration, let's say we start from 5, we find the fx, okay, f prime x, f double prime x. We can approximate
the screen is not on.
Oh, sorry. Okay, this one. Okay, we start from 5. And then we evaluate the objective function value and derivative at that point, and second order derivative at that point, okay? Then we use Newton method to evaluate the next point. Okay? Then we move to 3.8, right? Again, at this point, 3.838, yeah. You evaluate the fx, f prime x, f double prime x, okay? And then you can move to the next point, minimum point, and then closer and closer, okay, until you reach the minimum point. And the algorithm stop. Okay, so we finished the today class. If you have any question, you can ask, okay? And well, look at the code I sent you via Line group and learn how to, what's it, the algorithm, okay? How each algorithm works.
Sir.
Yes.
How would the midterm be?
The midterm, yes. I have to ask for a convenient time, okay? Your convenient time. Bioenergy, okay? So, okay, I will create the, what's it, when to meet survey, and then, well, I will put that survey in the Line group and ask everyone to participate in that survey, okay? For midterm exam, it encompasses the problem formulation, okay? Optimization problem formulation, and classical technique for optimization, and linear programming, okay? For nonlinear programming, well, we will deal with it in final exam, not during midterm exam, okay? That means the content from this class will not appear in the midterm exam. Okay. And yes.
Oh, sir. So just problem formulation, classical technique, and linear programming.
Yes.
So the thing that we learned today is linear programming, right? And the thing that we learned last time is classical technique.
Yes.
I see.
Yes.
In the exam, is it how would it be like? Is it, writing on paper or a computer?
Yeah, that's interesting. So okay. The first part is a multiple choice, which consists of 26 questions. In that part, of course, you can, because it's multiple choice, I can use any web-based system to handle it. However, we have 3 more questions that, well, you have to explain each step to solve the problem and explain me every step of the solution. That case, I think you can write on your iPad and export to PDF file and send me back. Alternatively, you can write on paper and then scan or take photo and send me back. It's okay. Yes. So I told you already, the midterm exam consists of 2 parts. Okay. The first part is multiple choice. Okay. 26 problems. And the second part we have 3 problems. Okay. And you have to write down your solution, explain every step of the solution. Okay. Any more questions?
Sir, so we explain the steps to our solution, but do we need like the actual solution too?
Yes, of course.
Okay.
It depends on the question. If I ask you to formulate the optimization problem, you stop at the resulted optimization problem. Okay. But if you are asked to solve the following problem and obtain the optimum point, of course, you have to show me how you get the result. I mean the minimum point or maximum point.
We can use MATLAB, right, for the optimization problem.
Yes, you can use MATLAB. But you have to explain me how you get the solution, not just show the problem and then just show your solution. It's not acceptable. You have to explain how you get those solutions.
What is the time limit for the midterm?
I think 3 hours enough, right? Enough.
Yes. Not on site, right? It's online.
Yeah, online is okay. Yeah, but if you want to work here on site, of course you can come. Of course, it depends on the time. If you it depends, because if you yes, you can write on iPad and then send back the solution, or you can write on paper and then take photo and send back the solution. Yes. However, for the multiple choice part, I think it's more convenient to do it on web-based system, right? You just select. Yes. Okay.
Teacher, do you have the O exam for everyone to practice?
I think you can practice on those example I gave you, because what is it? This one I can tell you that it's much easier than the previous case. Okay, much easier, but of course you have more problems to do.
Okay, teacher, thank you.
Yes.
There are the 26 questions. Does it cover all 3 topics?
Yes. Also, those 3 problems cover all three parts. I mean, three topics. Okay. The first one is on problem formulation. The second one cover the problem formulation and linear programming. And the last one cover the classical technique like Lagrange technique or KKT techniques. Yeah.
It is open book, right?
Yes, open book. Yes.
So how would the score be graded? Like, is it a curve or a percentage based?
I did not give you the course syllabus. Yes. Well, for those who, I mean, total score, if you get 80%, you will get A for sure. Okay. And then B plus, it depends on the the distribution. Okay. But if you get 80% or more, you will get A. Okay.
So how was like the last year people like? Is it a lot of B and C's and whatnot?
No, a lot of B plus and A. Yes.
Okay. Okay.
Yes. A, it's about 20%. And B plus about 60%. And the rest is B. Yeah. But you cannot compare with the previous year because, well, different sample, different population. Okay, so I think it's enough for today. Okay.
So last question.
Yes.
The unimodal, still unimodal. I still don't
unimodal, right.
still don't quite understand the definition. I was like, unimodal. So
okay, yeah, I can explain the mathematic expression. Yeah. Just one moment. Of course, you can read again, but I will try to explain it first. A function fx is unimodal if you look at x1 and x2 first. x1 is less than x2 and less than x star, okay, implies that fx2 is less than fx1. What does it mean? Okay, and the second condition is if you see a function fx is unimodal if the first condition, and the second condition is x2 is greater than x1, right? But less than x star, imply that if x1 is less than if x2, okay, where x star is minimum point. You see, if you take any point, for example, this x1 and x2, you see what happened to it. You can try different condition, but this condition, I mean, yeah, from theory, represent the idea where we have a unimodal function, and the shape of unimodal is in a certain, the given area, there is only one, local minimum point. There's no inflection, okay?
Sir, how is it that like one minimum can only have one minimum and like whatever maximum, or just like one minimum and cannot have any max?
No. You cannot have one maximum and one minimum. I mean local maximum, local minimum. You must have one local minimum. Okay. You cannot have both one maximum and one minimum.
So if we have one maximum and no minimum, and no local minimum, is that still unimodal?
Yes, but it's not minimum. That case is maximum.
Okay. Okay.
Mhm.
Okay, sir.
Well,
Understood.
you see that if we follow from the left hand side, if we go to the right, right? Let's say we are at A. Okay.
Yes.
And we move to the right hand side, and you see that the objective function become lesser and lesser, right? Smaller and smaller. Okay.
Yes. Yes.
And once you go beyond the minimum point, it is the opposite way.
I see.
Yes.
Okay. Okay. Sir, by the way, the midterm is next week, right?
Well, we can just one moment. We can have midterm next week or the week after that. What you want? We can have on what about 3rd of October?
3rd of October.
Yes.
What day would that be? 3rd of October.
Tuesday.
Tuesday.
Yes. What do you think?
Hmm.
Then we can skip the class on the
Can do the on to 10 October.
10 October. Yeah, maybe too far, right? So I don't recommend that. Yes. But for me, it's okay. But for you, I think, yeah, because of course, if the exam is on 10, right? Then you have class on another topic on 3rd. Yes. You have to learn another things on 3rd. Yeah. Then I will make survey again. And if you are okay with 3rd, then we can have class on exam on 3rd. Huh? Maybe this time it's okay. 4 to 7, yeah.
And Professor, will you stand by here?
I will be here if you want. But of course, you have to confirm that you will come. I don't want to stay alone here. If no one comes, of course, I will stay at home. Yes. But of course, because you can do it online. If you want.
I was trying to have a problem to get in the first lecture. With the next, and the software will work different tasks. In some cases, different tasks. In some different tasks. So I have to use the software. Yeah.
No. You don't need that. You don't need software. For the exam, you don't need it.
Sir, if we don't
Yes.
use software, right? How would we find the answer for like the one that we use MATLAB?
You can use calculator, of course.
Oh.
You can use calculator. You don't have to use the software.
But isn't the question too difficult? Like if you give
No,
us
it's not that difficult. It's very simple. Okay.
oh. So not like the Yao Mip questions like that, right?
No, it's very simple. You can use solver, but of course Excel solver you can use it, but you have to explain everything Yes. Also MATLAB, if you can use YAOMIP if you want, but as I request you to explain how you solve it, okay? So that will be very difficult. I mean, because you have to explain every step how you get those solutions, okay? Not just I put this command to MATLAB. No, it's not acceptable like that. Okay. Okay. Then, well, you have to, of course, you can, what is it? You can write how you solve that, and you can repeat the calculation again with your with MATLAB or anything to check the solution, the answer. It's okay. You got my point, right?
Mm.
Mm.
So,
That
so the MATLAB part is not necessary then for this midterm.
is not necessary.
I see. Okay.
Or you can solve it with Excel, but I can tell you that calculator is enough.
Mm.
Okay.
So we'll be mainly using the classical technique and linear programming to solve it if we are using the calculator.
Pardon?
So we're mainly using the classical technique and linear programming to solve.
Yes. Yes. Mm-hmm.
Mm.
You know, while I explained you 2 or 3 algorithms already about linear programming, right? To solve the linear programming, you can use graphical if you want. You can use simplex method. It's very simple. And of course, for simplex method, if you decide to use simplex method, you have to draw the table. Okay, show me the table, right?
Mm.
But in reality, of course, you can program those in Excel. Okay, and you copy those table from Excel to your answer sheet. It's okay. I don't care about it.
Okay. Let's see.
Okay, so well, it's enough for today. So have a good day, everyone. Oh, we have one question in the chat. Can we use other program, Python, Excel? Yes, you can use it. Okay, but in the answer sheet, you have to explain how you solve the problem. Okay.